Welcome to Chemistry 111. Uh, we're going to continue with Chapter 6 in a little bit, but first I'm going to answer a question about homework that could be relevant to the test from Chapter 5. Later today, I will go ahead and post a video crib to the Chapter 1, to the first test. I mean, better or worse, I've given people a week and a couple days to get that test in. If you haven't got it in, it is what it is. At this point, it'd be like 45 points off. So not sure you're getting much points if at that point anyways. But okay, let's go to, I gotta switch over real quick to Q. Okay, so right here we have on this problem, a space probe identifies a new element in a sample collected from an asteroid. Successive ionization energies in attajoules, which is like we talked about nano. Well, you keep going down, you'd have pico, and I think I'm trying to remember, there's a couple other units, but attajoules is a really, 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 really small unit. But you're talking about attajoules per atom. So it's a really small unit, but we're talking about individual atoms. So for the new element given on the table, the ionization energies, to what family of the periodic table does this new element belong? So the options are 1A, 2A, 3A, 4A, 5A, 6A, 7A, or 1, 2, 13, 14, 15, 16, 17. There might be 8A down there as well. I can't, my thing's lagging real quick, so it may there, but hopefully you can still hear me, and it's not a problem while this is loading. So what you got to remember is the 1A, 2A, 3A group has to do with the valence electrons and the s and the p orbitals. 1A and 2A have respectively one valence electron in the s and two valence electrons in the s. Group 3A, 4A, 5A have two electrons in the s and then one in the p, two in the p, three in the p. So for a total number of valence electrons equal to the number prior to the A. So 5A has 5 valence electrons. 6A has 6 valence electrons. Now, we just previously talked about in this chapter the octet rule, that an atom will either want to achieve 8 valence electrons or lose all of its valence electrons. So if it's in group 1 or 2, it'd probably want to lose either its 1 or 2 valence electrons rather than try to gain 6. And if your element like 6 or 7, it would be easier to gain 2 electrons or 1 electron than it is to lose all 6 or 7. However, it is still possible to lose all 6 or 7. So what we should have been looking at is, what is the group number versus what is the likely charge? So a 5A element would rather be 3 minus than 5 plus, which became relevant on some of the test 1 stuff. But okay, so the ionization energies, the whole idea is, when you see a huge jump in ionization energy, you have gone from what's called the valence electrons to the core electrons. Once you remove all the valence electrons, the next electron lost is a significant increase, because the core electrons are closer to the nucleus and thus are more strongly affected by the nuclear attraction. So it takes more energy to extract them. It's like, how easily can the atom watch over the electrons when they're out over playing at a friend's house next door versus playing in your backyard? You can look out of your window and look at the child in the backyard, as opposed to, well, I think they're still at the friend's house, assuming they haven't gone riding down the street or something like that. So the closer they are, the harder it is to, say, extract them. So in my particular problem, which may be different from your problem, but my particular problem says the first electron is 0.5. The second electron is 1. So it's increased by a factor of doubled. It's gone from 0.5 to 1, so 1,000. And then it goes from 1 to 4. Now, so it's more than quadrupled in size in this case. However, I'm going to check the other ones just to make sure. So 1 to 4 might be my big jump, but I'm going to double check. And it goes from 4 to 5, so it's only jumped by 1,000. 5 to about 6, it's only jumped by 1,000. 6 to close to 8, 7.9, it's only jumped by 1,000, maybe 2,000. Almost 8 to a little bit over 8, so it's jumped by far less than 1,000. So based on this, where's the biggest jump? It's between element 2 is loss 2 and loss 3. So losing 1, it's easy. Losing 2, it's easy. Losing 3, it's hard, which means how many valence electrons is it likely to have? I would say it would have 2 valence electrons. 2 valence electrons puts it squarely in the 2A column. So the last easy electron to remove is going to be where the column's at. So if it's easy to lose only 1, and then there's a huge jump and followed by like smaller jumps incrementally going down, then it'd be group 1. If there's 3 easy jumps, and then the 4th one is too hard, then it'd be in group 3A, so on and so forth. You could have 7 jumps, and then the next one be, instead of 79, be like 15. And like, oh, that 3,000 jump is nothing compared to that 15,000 jump. And then maybe we're at 7A. So hopefully
so the I2, isotope 2 and isotope 3,
that's ionization 2.
Yeah. It correlates with the column.
Yeah. So okay. The ionization 2 says I've lost 2 valence electrons, and it's easy to lose those 2 valence electrons. Now, because it's hard to lose the 3rd electron, that 3rd electron must not be in the valence shell. It must be in a core shell electrons. And so which elements have only 2 valence electrons? And that's where we go to, oh, it has to be 2A. So we're looking at which core, where's the valence and where's the core? Where's the valence and where's the core? And the easy loss is always from the valence. The hard loss is from the core. So we have to count how many easy losses we have to figure out which column it would be in. And that's what you'd have to do. So yours may be the big jump is between 3 and 4. Big jump might be between 4 and 5. It all depends on what you have, but it's essentially like that. So there's like many different versions of that. Okay. Now, we can always come back to this. If we have any questions near the end, I can slow down because I'm sure we're probably well past where we're supposed to have been in the notes, all things considered, even though we are dealing with the snow. Okay. So now this concept is something that will build on the stuff we have just been discussing, and this is electronegativity. It's kind of a combination of the ionization energy and the electron affinity that we're just briefly discussing. Ionization energy, remember, is the energy required to remove an electron from a gas phase atom. Electron affinity is the energy gained by giving an electron to a gas phase atom. Well, electronegativity is the ability of a bonded atom to attract a shared electron through a bond. So previously, it's just giving a naked atom an electron or take an electron from a naked atom. Now we're talking about bonded atoms. But the whole idea is the easier it is to be ionized, the harder it is to get an electron, the weaker it is at holding on to the electrons it has. The harder it is to ionize, the easier it is to give an electron, the better the atom holds on to the electron. Essentially, electronegativity is a giant tug of war. You have this bond is a rope between the two atoms, where an equal sharing of electrons puts the electrons squarely and the knot in between them. They're equally matched. They spend the time exactly in the middle. However, certain atoms have better electronegativities than other atoms. And so when it comes to the sharing of electrons through this bond, the electrons get tugged more to one side than to the other. And so this will create some sort of charges that we'll deal with next semester, such as dipole moments and dipole-dipole interactions and hydrogen bonds and all sorts of fun things when we talk about why does water have these properties, but oil has these properties? Why doesn't oil and water mix? And it has to do with these electronegativities, because oil is typically made of mainly carbon and hydrogen. Carbon has electronegativity of 2.6. Hydrogen has electronegativity of 2.2. The difference between those two is 0.4, and it's really small. Water has electronegativity of 2.2 to 3.4, so a difference of 1.2. It's a pretty big difference as opposed to the really small difference of 0.4. And so this difference in electronegativity is going to be responsible for water dissolving all sorts of things. If you'll notice, the metals, lithium, beryllium, and even some of the transition metals have a lowish electronegativity. All those blue atoms are metals with our low electronegativity. The green atoms are metalloids. They still have a lowish electronegativity, but it's starting to creep up there. And our nonmetals in the kind of golden yellow, or kind of at least tannish yellow, are nonmetals with the higher electronegativity. Now, to measure the electronegativity, we're going to be measuring the differences between those two atoms. But the three ones you really need to pay attention to are nitrogen, oxygen, and fluorine. Those are the big ones. However, chlorine and bromine kind of have an effect. But nitrogen, oxygen, and fluorine are typically the really big ones you need to worry about. Fluorine being the highest. It would more rather pull an electron through a bond than share any of its electrons. But generally, atoms with higher electronegativity tend to have more lone pairs. Elements with lower electronegativity tend to be the central atom. So when we draw these Lewis structures, the low electronegativity atoms are usually in the center. The high electronegativity atoms are usually around the borders, and they have a bunch of lone pairs associated with them. Okay, let's see. Let's see. We're gonna load the next screen. Okay. So now here's a new concept we have to put into our Lewis structures. And this is a formal charge. There's a difference between a valid Lewis structure and the best Lewis structure. When we have multiple different possible structures, not all of them are equally stable. A formal charge is a type of electron bookkeeping where we're going to help determine which atom is the most stable. How to calculate a formal charge? It's a hypothetical charge you put on an atom of the Lewis structure based on how many more electrons or less electrons it has than its valence number. So this once again comes back to the whole valence idea. Nitrogen is group 5A. It should have 5 valence electrons. So based on the electrons you've drawn around them, how many of its 5 valence electrons does it have? Does it have 5, in which case the formal charge would be 0? Does it have 6? Well, then it would be -1. Does it have 4? Well, then it would be +1, and so on. Oxygen with group 6A should have 6 valence electrons around it. So depending on what structure you have, you may have neutral or a formal charge of plus or minus. So to calculate this, you're going to count all the lone pairs and half of all the shared electrons, so half of all the bonds. So a bond of 2 electrons would be count 1 for oxygen and 1 for whatever it's bound to. And then we'll have to compare them to their valence electron count. Now, please note, the sum of all formal charges should always add up to the overall charge. So if you have a charged structure like nitrate, there should be at least one formal charge to give it a -1 structure. But you could have 2 negatives and 1 positive, because -2 plus +1 equals -1. So you will have at least one formal charge, but maybe more than one, so it adds up to the overall charge. If you have a formal charge of -1 and +1, it would match a chargeless structure. But generally speaking, the most stable structures, if there's more than one possibility, will have the lowest formal charges, or no formal charge at all if you have an option. However, if you have to give a formal charge and you're trying to determine which one is the best, putting the negative charge on the atoms with the highest electronegativity and the positive on the atoms with the lowest electronegativity is the best option. So if you're having a charge, having the option of putting a formal charge here versus there, you want to go back to that table here, where you look at, oh, carbon would be more likely to have a positive charge than nitrogen. Nitrogen more likely a positive charge than oxygen. Oxygen more likely a positive charge than fluorine. Oxygen more likely a negative charge than chlorine. And so depending on what you have, but chlorine would more likely have a negative charge than nitrogen. Sulfur is similar to carbon. So we're going to try some structures with this. So nitrate. I have nitrate, thiocyanate, and azide. So we've kind of done thiocyanate before, but we'll look at this again now using this formal charge idea. So go into here. Oh, crap. Go into the dot cam. So first thing first, remember our rules. First, count the number of electrons. Nitrogen, group 5, so it has 5 electrons. Oxygen, group 6, so it has 6 electrons. 6 times 3 is 18, and then it's charged, so +1. So 5 plus 18 plus 1 is, what, 24? 24 electrons. Now, which guy can make the most bonds? Nitrogen guy comes first in the formula. Nitrogen. Which guy is the least electronegative? Nitrogen. So nitrogen is going to be our center. Oxygen is going to be around it. Let's put 3 oxygens around it. And we're going to put 3 single bonds. 2, 4, 6. Now we have 18 electrons left. Each oxygen wants to have 8. Each oxygen wants to have 8. So Each oxygen currently has 2. So let's use 2, 4, 6, 10, 12, 2, 4, 6, sorry, 8, 10, 12, 16, 14, 16, 18. I'm having some trouble counting. So right now, each oxygen has an octet. How many electrons does nitrogen have? 2, 4, 6. Now, since we have the option, we're going to try to give the nitrogen an octet. So how do we do that? We can take electrons from any one of these 3 oxygens and pull them into a double bond. So I'm going to pull this down. We have double bond now, and I'm going to scribble these out. This oxygen still has 8 because 2, 4, 6, 8. Now this nitrogen has 2, 4, 6, 8. Now, there should be a charge on this structure because it's nitrate. Now, let's look at what all the formal charges look like. Now, oxygen, remember, group 6A, it has 6 electrons. How many electrons does this oxygen have? 1, 2, 3, 4, 5, 6. It's an octet with a formal 0. Because it's supposed to have 6, it has 6. This oxygen, 2, 4, 6, 8, has octet, formal charge of 2, 4, 6, 7. It has 1 extra electron, so a formal charge of -1. The same thing for this oxygen, formal charge of -1. Now let's look at the nitrogen. 1, 2, 3, 4. Nitrogen has an octet, but it's a formal charge. Since nitrogen is group 5 and it has 4 electrons coming directly from the nitrogen, it would have a formal charge of +1. 1 electron shy of what it should be, +1. Now, when we add this all up, +1, -1, -1, they add up to the total charges of -1. So nitrate structure has 2 negative formal charges and 1 positive formal charge on the nitrogen. But that is the most stable structure. Try drawing another structure that doesn't have that situation going on. Now, thiocyanate, going back up here. Sulfur is group 6. Carbon is group 4. Nitrogen is group 5 and 1 electron. 6 plus 4 is 10, plus 5 plus 1 is 16 electrons. So let's draw this guy. Carbon is in the center. Nitrogen, sulfur. Single bond puts us at 12. 2, 4, 6, 8. 2, 4, 6. What am I am not counting good today. Now, remember, we had 3 different options here. Let's draw the 3 options. We had this guy. We had this guy. So draw the lone pairs. And I'll go ahead and put the 3rd option down here. S, C, N. 1, 2. Okay, we have these 3 options. Which one of these 3 options is best? Now let's look at these 3 options first with respect to the carbon. Carbon should have 4 valence electrons. In all 3 of these structures, carbon has 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. In both of these structures, carbon has 4 valence electrons. So there's no formal charge on the carbon. Now, depending on which structure we have, there may be formal charges on the sulfur and the nitrogen. So let's look. In this structure, 1, 2, 3, 4, 5. Sulfur is supposed to have 6. So we're putting a positive 1 on the sulfur. Nitrogen should have 5. 1, 2, 3, 4, 5, 6, 7. So the charge is on the -2 on the nitrogen. +1 and -2 add up to -1. Look at this structure. 1, 2, 3, 4, 5, 6. 0 formal charge on the sulfur. 1, 2, 3, 4, 5, 6. -1 on the nitrogen. 0 and 0, 0 and -1 add up to -1. And finally, this structure down here, 1, 2, 3, 4, 5, 0 formal charge on the nitrogen. 1, 2, 3, 4, 5, 6, 7, -1 on the sulfur. 0, 0, and -1 add up to -1. So if I was to choose the best structure of all these, it would be the one with the lowest formal charge, which comes down to those two, and has the formal charge of the negative on the most electronegative atom. So which is the best structure? Nitrogen is more electronegative than sulfur. So which structure is number 1? I would say this guy is number 1. If I would say the second most stable structure, I would say this guy is number 2. Even though we put the negative charge on sulfur, which is less likely to want it, this guy has 3 formal charges. This guy has 3 formal charges. This has more formal charges, so it's less stable. Even though you have a positive on the sulfur and 2 negatives on the nitrogen, greater formal charge means lesser stability. So this guy would be the most stable Lewis structure, the best Lewis structure, second best, and then the worst, but still a valid Lewis structure. If I said draw a valid Lewis structure, any of those would work. Now, N3 minus is going to be just like thiocyanide, except with all nitrogens. And this is a linear molecule. This is a one that organic people sometimes have to deal with. N3, which is going to be 5 times 3 plus 1. So 16 electrons again. N. That uses up 4. So we're at 12. Same setup as our thiocyanide. It uses all the electrons. Then we have to make some sort of bonding. So which would be the better structure? So technically, there's only 2 structures in this one, 2 possibilities. We could do this guy, where I've taken a lone pair down from here. A lone pair down from here and a lone pair down from here. And move them to the double bonds. Or I could take 2 lone pairs from the same nitrogen down. Both of those are valid structures. So, but let's look at the stability of these guys. No matter what, this is not super happy. This nitrogen, 1, 2, 3, 4, 5, 6. Formal charge of -1. Formal charge of -1. Formal charge of 1, 2, 3, 4. +1, because each nitrogen should have 5. That's 6. That's 4. That's 6. -1, +1, -1 adds up to -1. What about this structure? 1, 2, 3, 4, 5. Formal charge of 0. 1, 2, 3, 4. Formal charge of +1. 1, 2, 3, 4, 5, 6, 7. Formal charge of -2. Even though this one they all have the same number of formal charges, this has the formal charges maybe a little bit more spread out, so this one might be a little bit more stable. A little bit more stable. However, we often adopt this structure prior to a reaction because this azide in organic chemistry is often used because it can put a nitrogen on and then breaks off to release nitrogen gas. But that's not for us to worry about right now. That's future chemist problem. Okay, come on. Got to... Come on. Oh, yeah, my computer's going so slow right now. Okay, thank God. Okay. So we can use this formal charge on most of the structures we've already seen. But this is going to be very useful when we comes to looking at some of the polyatomic ions, such as sulfate and nitrate and... Oh, come on. Okay. So looking back at our rules, valid Lewis structures now must all valence electrons from the atoms. We must count all the valence electrons from the atoms and adjusting for ionic charge. All atoms should have octets or duets. And we should also have small formal charges with the sum total is no greater than the overall charge. Finally, if I ask for more than one, you should try to include all reasonable resonance structures. Some questions may ask for more than one structure. Some of them may just say, what is a valid Lewis structure? All depends. But sometimes you may need to draw more than one. But we're going to keep adding to this as we go because there's some more rules. We're going to start easy, and then work our way up. Try not to overload you all at once, but we have to be able to draw these structures. These structures are going to help us later on, especially if you need to take any more chemistry after Gen Chem 1 and Gen Chem 2. You do need this for organic. I know it's like a lot. You need to be able to understand this. If you're trying to understand anything about biochemistry, you need to understand what the molecules look like and why they're built this way. And we can't look at essentially the 3D models until we understand how to even draw the structures and what they should look like. We can put a bunch of letters together in a structure, but without being able to actually understand what they're doing, can't go beyond that. Now, the next thing is we're going to talk about the exceptions to the octet rule. There's usually two major exceptions. One of them is going to come up a lot more than the other. Now, while we are going to try to achieve the octet rule as often as possible, you can have situations where you either have an incomplete octet or an expanded octet. Now, molecules with the incomplete octet just don't have enough electrons to get the center atom an octet. The most notable examples are group 1, group 2, and group 3. Group 1 and group 2 are metals, and they will be in ionic bonds. But group 3 boron is going to be the one where, like, remember we looked at borane, BH3, and BH3 just had 6 electrons. There was no way to give it 8. Boron just cannot get that 8 without doing something funky. And most boron related compounds will have that issue. It doesn't have enough electrons to give it an octet without breaking some other rules. Now, nitrogen compounds will sometimes have that problem because many nitrogen compounds have an odd number of electrons. Whenever you have an odd number of electrons, there will be a radical. A radical is an unpaired electron. It's not an alone pair, it's an electron by itself. And this radical is highly reactive and responsible for a lot of the crazy chemistry we have going on. The reason why nitrogen pollution out of our vehicles is so dangerous to the atmosphere is because we're producing nitrogen radicals. Nitrates, nitrogen trioxide, nitrogen dioxide, this nitrous oxide gas, full of radicals that can do a bunch of atmospheric chemistry and break down our ozone layer and all that jazz. It was at this point that my system completely freaked out and kicked me out of Google Meets. It did not let me know. It had kicked me out of Google Meets. I was kept on lecturing for another 10, 15 minutes until I came back to check on everyone and saw that I was no longer in Google Meet altogether. So this is where we will go ahead and end the lecture. We will pick this up on Monday and have to deal with it as we deal with it. Hopefully this doesn't happen again. If so, we'll sort this out, find a way to keep this from happening again. But in the meantime, this is Professor Evans signing off.